So hello and welcome to Unit 1.5. If you are on the J277 specification, so it's the year 2020 right now. If you're currently in year 9, then this will probably be Unit 1.3 for you because the course has slightly changed. But for those in year 10 or 11 of 2020, then you'll be on J276 and this will be Unit 1.5. Network topologies, protocols and layers. The real fun stuff of networks. So in this computer science GCSE there are 2 units on networks. The first one we have looked at, unit 1.4, which is all about wired and wireless networks, and now we're moving on to maybe the more technical details such as network topologies, protocols and layers. So we're going to start by having a little look at some network topologies. So, most computers and devices are connected together via networks. This opens up new opportunities and advantages. What are the advantages? Well, I can think of a few right off the bat. I mean, you wouldn't be watching this right now if you weren't networked. If you didn't have a device that could connect to a network, that could connect to the internet, then you wouldn't be able to watch this video. So communication is a major thing, being able to share data, whether that's video data, images, text, messages, all of that allows you to communicate effectively, and at the kind of click of a finger, it's there. We can also work collaboratively, so we can create things and work on them together at the same time, which is pretty impressive. And we can also share things as well, so peripherals like printers or scanners, those kind of things you plug into a network and then you could use it from anywhere, much like you would be able to at school. So that's the big picture. Learning objectives. You'll be able to identify a star and a mesh topology, you'll be able to compare the advantages and disadvantages of Wi-Fi and Ethernet, and you'll be able to understand and explain what encryption is and why it's required. So, what is a network? A computer network is a number of computers linked together to allow them to share resources. Networked computers can share hardware, software, and data. That's something I didn't really talk about, but software as well as data, being able to share a bit of software, access it from any device is really, really powerful, and that's from BBC Bite Size. So, remembering that computers are linked together when describing a network is really important. It's something that's really obvious, but that could get you a mark, and so it's worth remembering the basics, like a computer network is a number of computers linked together. It sounds obvious, but that'll get you a mark. Okay, we are going to ignore that. Okay, keywords. Topology, mesh network, star network. So we're going to move on to the rest in a second. Let's don't worry too much about these keywords for now. So let's think about the word topology and mesh and star network. So let's come over to where we were last lesson. We were looking at URLs, we were looking at domain names, and we were looking at this idea of a domain name system server. Or a DNS server. So when you, in your house, on your laptop, you type in ocr.org, it gets sent, what we're doing in Instagram, we're beaming it to the WAP sends it through to the switch sends it to the router knows, it doesn't know where ocr.org is, but it knows a DNS server who knows where it is, so it sends off our ocr.org through the internet to the domain name system server. It has a little look, OCR, yep, that's in my domain names, and it returns you the IP address associated with that. So it returns 230.8.99.17 through here, all the way back from the router to the switch, to the WAP, across to your laptop, and the laptop now has the IP address 230.8.99.17, which it can then communicate with. So then it sends off a request to 230.8.99.17, so it sends it back to the WAP, back to the switch, back to the router. The router says, I know where that is, and forwards it on through the internet. Number of hops later, it pops out the other end at 230.8.99.17, and it can then get the web resource from a server located on this network. So let's imagine this computer was the server. It would then respond by sending the web page back through the internet and back to my computer. Now, these networks are laid out, they have a certain layout. The way they're connected together the way it looks, they have what's called a topology. And a topology, let's grab my brush. A topology is just the way something is laid out. So it just describes how a network is laid out. Now there are two main types of topology. The first one is a star topology. And the second is a mesh topology. So let's start with a star. So if we were to have a star, we would have a central node. Now this node could be a server, could be a router. I'm just going to draw a kind of box to represent something central. Okay, and let's annotate this as well. So that is my central node. And this could be a server or a router. And then to make this star topology, all we would do is we would just connect everything to this central node. So if I jump back to white, let's just plug in a few things. I'm going to draw a few very bad laptops. Now, it gets its name star because you kind of have these branches coming out of it that could resemble a star. But in topology sense, this is kind of, I don't know, it's not describing how it physically is laid out. So you could have a star topology that doesn't actually take the shape of a star. Star is just kind of used as a general name to represent it, much like a heart symbol doesn't actually represent the kind of shape of the human heart. The star topology isn't. Don't get too caught up on the fact that it should be in a star. But for diagramming purposes, you would try and draw it in a star. Now, I've drawn an upside down star. Really, I should have put this one at the top, but I've done my title too close. And let's draw another laptop here. Obviously, these laptops, these are just nodes. They could be computers, they could be phones, they could be anything you like, really. So these are all plugged into the star. All plugged into the central node. Now these are all clients. But don't get this twisted with the client-server model. Now, the client-server model is something we will have looked at already. And maybe I'll just write kind of client-server model, and I'm going to put a big cross through that. So this is not the client-server model, okay? This is a topology of how this is laid out. The client-server model talks about how data is shared on a network. We are talking here about how a network is laid out. You could have a client-server model laid out as a star or a mesh topology. So they're two very separate things. And the peer-to-peer model, you could have laid out in either topology as well. No, I don't think you could have a peer-to-peer as a star. But anyway, so we've got our clients around the edge here. We've got a central node, which could be a server, could be a router. These lines here, these are direct connections. Which means that each client, each node on that outside here, has a direct line into the server or the central node, which is kind of important because that connection is going to be faster. There's going to be less traffic on it. So that will have less traffic. Can we move along here a little bit? Yeah. That will have less traffic. but it is a single point of failure. So if that connection was cut, this laptop would no longer be able to connect, or this node would no longer be able to connect to the central node. Okay, as soon as this gets a cut in it and it's broken, then we have a problem. Now, the good thing is that this doesn't affect other nodes. Okay. No effect on other nodes. So even if this cable's cut, this, and this all have their own secure connections that haven't been affected. Okay, let's have a little look at a mesh topology then. So we still have a server. In fact, we might have a couple of servers or specific nodes that computers might attach to. So let's say we have a server here, and let's say we have maybe a smaller server here. And then we have, I'm going to represent all nodes by laptops, but just know that this really is just representing any device capable of being networked in and wired. Okay. So the way a mesh network works is just that. It just creates a mesh between the devices. So devices are capable of receiving more than one connection, and those connections can be kind of between those that they share the most data with. So if I decided that actually this laptop, this node up here, really only needs to speak to this laptop or this node and this node, then I'd connect those two together. This node might need to connect to this server and this node. This node might need to connect to here and to here and to here. And then let's say this node might connect to this node to this, and then him to him, him to her. Okay, so you can see here that we can kind of build up this mesh network with the nodes. I need to stop calling them laptops and computers. With nodes or clients connected to those that they share most data with. So they don't all connect to a central point. They can connect to just kind of the thing that's easiest to connect to, or the thing that's most reasonable to connect to. Okay, if my computer in my star network over here really only ever needed to talk to this computer next to it, but always had to go through the server, the system could be made more efficient by putting a line in, cable in, connecting them directly. Now, this would stop this being a star topology and take it more into the realms of being a mesh topology. So with a mesh, we have redundancy. Where's my hand? There it is. So if we have a look at, let's say, this connection or this connection here. So if we broke this connection, we still have redundancy. And what we mean by redundancy is that if we have more than we need, okay? If you get made redundant at work, it's because they no longer require you to do the job that you need because it is not necessary. And this cable isn't necessary, because we can still connect. If this computer wants to, or this node wants to talk to this node, it could go down to here, and then it could go up to here, or it could go down to here, up here, across here. So it's got a few paths, and that is what we mean by redundancy. We've got more than we need, and so this stops this being a single point of failure, and allows us to, if we were to kind of lose a connection, we'd still be able to communicate with our devices. Now, this would need more cabling, so it would be more costly. Although arguably you'd probably need less cabling because you might not need to run them as far. Yeah, let's not go into cost. Actually, I think it might be 6 of one and half a dozen of the other. But we got redundancy there. However, we're probably going to have higher traffic, especially for something like this node here. Instead of just having a nice direct line like we have over here, straight to the server, okay, we've got shared lines now. If everything's trying to talk to this server, they're going to have to share these lines that go into the server. And so here and here are going to be high traffic areas, and so lots and lots of data is going to be zooming between them that could slow things down compared to our star network where everything has a nice direct connection. So this is a shared connection. So let's see what OCR have to say about star and mesh networks. So they say a mesh network is where some or all of the workstations or other devices are connected directly to each other. Most are usually connected to the node they exchange the most data with. A star network, on the other hand, each device is connected by an individual cable directly to the server. Star networks are usually the layout of choice in schools and offices because they tend to be most reliable of the topologies. And they're reliable because if one cable goes down, then that's not the end of the world. They've got this direct connection, so they've got the fastest transmission speed possible from one node to the central node, and so there's not going to be this kind of high traffic area. Obviously, once you get to the server, it's still got to process all that data, and so there still could be kind of a choke point, but the choke point won't be in the cabling infrastructure. And so this is what we mean by topologies, the way a network is laid out. And this tends to be the physical layout of the network, but it might not look exactly like a nice star or a kind of meshed grid. It might look different in practice, but in theory, these are your kind of diagrams for if you were to draw a star network or draw a mesh network, you would have something like this. Okay, so if we do a little zoom, let's fill the screen. Fit screen. Okay. Nice. And so you can see here there's kind of elements of us having a star network in our LANs that we've kind of made. Imagine the WAP and the switch were part of the router. Then everything would just be connecting to the router. Really, the switch and the WAP are just extending the functionality of the router. And so an argument could be made that these three serve as you could abstract them as one device, which everything is connecting to, one central device. Yeah, because essentially the WAP and the switch are just allowing connectivity to the router. Okay, so that's what a mesh network is, that's what a star network is. Okay, so I'm going to change my screen to a selection of cards, and what I'd like you to do is write the heading of Ethernet features, write the heading of Wi-Fi features, and I would like you to put the corresponding phrase, I guess, under the corresponding heading. These are doubled up, so you can ignore one half of these are just a copy for printing purposes. So Ethernet features, does it have a stable connection? Does it have cheap setup costs? Does it have reduced possibility to be hacked? And you're going to put these different features under whether it's an Ethernet feature or a Wi-Fi feature. None of these are for both. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 cards, 15 phrases. And I'd like you to put them one under either under the Ethernet features column or the Wi-Fi features column, and you'll have to hand write this because unfortunately this is the internet and I can't give you a physical printout, but you can write this. And if you pause the video here, we will then go through the answers once you have done this yourself. Okay, I'm going to trust you and hope that you did that and you paused the video. If you haven't, do it now. Let's go across to our PowerPoint and let's have a little look at the answers. So we had the cards, you've written down whether they are features of Ethernet or Wi-Fi, and now let's have a look. So Ethernet benefits. Ethernet is a stable connection. There is a reduced possibility to be hacked. In here, if we zoom in, when you are broadcasting data across the airwaves here, if I'm sat somewhere in the vicinity with some kind of device that can kind of pick up radio frequency, radio signals, then I might be able to read your data as it's coming in, and then I could maybe do something with that. And if you were sending unencrypted things through your wireless network over the radio waves, then I might be able to actually intercept those and take them and start reading your data, and it could be passwords or bank information. So there is less possibility to be hacked because I can't do the same thing in a cable. I'd have to physically plug myself into the network to be able to mimic any of that behavior that I just talked about with intercepting radio waves, because they're not broadcasting it through the airwaves. It's more secure, so that kind of comes into reduced possibilities to be hacked, really. Faster traffic speed, so it's much faster just to send directly through a cable than to beam it through a radio wave through the air. And that's because, well, things move quicker through solids than gases, so that'll be one reason why kind of sending something through a cable will be faster than sending it through the air. But also, they're having to convert it to a radio frequency, send it, receive that radio frequency, and then kind of be able to send that on is going to take more time than just sending it through a cable. Generally, we'll have a good quality signal. So Ethernet is normally the signal from one end and another, regardless of whether there's walls or whatever's in the way. Generally, it will be fine. Yeah, I'm not going to go into why it might not be fine, but it will generally have a good signal quality. Wi-Fi, on the other hand, is very cheap to set up. Everyone who has a Wi-Fi enabled device, they don't need cables or anything, so they can just connect to the Wi-Fi network and be set up. It is more vulnerable to hacking. If you've got walls, if you've got LED paneling, if you've got kind of different floors in your house, you've got distance, then the signal quality will reduce over distance and obstructions. You can connect multiple devices without the need for extra hardware. So here, I can connect 2 more devices until I need to buy another switch. Whereas my WAP should be able to accept, like 50 wireless devices and not really be affected too much. Obviously, there is a certain amount of devices that a single WAP can take realistically, but I don't think that will come up in your exam. So your WAP can accommodate much more devices than a switch does, so you wouldn't need to buy any extra hardware. Interference can occur with Wi-Fi. So if I had a kind of microwave here and I was microwaving something, I might find that there is some interference with my Wi-Fi. If I had other people communicating on the Wi-Fi as well, that might interrupt my radio waves, and so there can be interference on the line. There is less disruption to the building due to no wires being installed. So in my LAN here, I'm having to run all of these cables everywhere to my computer, to my printer, to my WAP. But the wireless devices, they don't need anything. I can just walk around and connect to it. So I don't need to worry about kind of configuring this. And in this LAN here, this could be a two-story house, and these could be kind of far apart from each other, and could, the cables can't just be run across the floor. They need to be hidden maybe under the floor or in the wall or in trunking in a kind of plastic tubing that is screwed to the wall. And so there's a lot less disruption just connecting wirelessly to a WAP. User not tied down to a specific location. So when I'm at my computer, I'm at my computer. But when I'm on my phone, I can be on the train, I can be wandering around town, I can do whatever I like and have the freedom to roam. I may not be able to receive signal. So if I take my phone and I go off and I walk away from my WAP, there will be a point, if I keep walking, where I disconnect from the network. So I might not be able to I might be too far away from it, and I might not be able to receive the signal. The connection is not as stable as wired networks and can drop off. So the connection could kind of fluctuate. Oh, hello. And it could be affected by the amount of users, by the other interference in the area, as well as the obstructions and your distance. So there's a lot that can affect your connection that you just don't get with Ethernet. And it tends to have slow transfer speeds. Now, they've called this Wi-Fi benefits, and under the benefits of Wi-Fi, they've put more vulnerable to hacking. I wouldn't say that's a benefit. I'd say that maybe they've got this a little bit backwards. Interference can occur. I don't think that's a benefit. May not be able to receive signal. So I think this is maybe this should be features. I think in the worksheet it was features. Yeah, features, not benefits. So hopefully you put features at the top rather than benefits, because that's not a benefit. So there we are. Slow transfer speeds, obviously, I kind of touched on earlier. It's much faster to send something directly through a cable than through the air as a radio frequency, which has to be sent in a specific way, received in a specific way, and then sent through a cable anyway. So it's going to be much quicker just to send it through a cable in the first place. So that's our benefits of Ethernet and Wi-Fi. So Wi-Fi stands it's wireless frequency. If I were you, I'd do some research on maybe where Wi-Fi comes from, but as far as I know, it's kind of just a made-up thing that doesn't really stem from anything. But wireless frequency is good enough for us. Radio waves are used to transmit data packets without the need for wires. This method is slower and more vulnerable to attack, but it removes the need for cabling and networks. This means that it can be set up in remote locations, such as in vehicles, in parks, or on planes, etc. Okay, there is a video here that I will include in this video's description. I would say only watch it if you are really interested in Wi-Fi frequencies. So just to kind of go through a little bit about Wi-Fi frequencies and how it works, we have I got much space on here? Yeah, I've got a little space in the corner. So we have a radio frequency, and it is just a wave like a sound wave. Okay, so our wave diagram, we have a line here, and our wave can look something like this, where it comes up, over and down, and that, let's say, is 1 second here. Okay, so 1 second. So this wave has repeated itself after 1 second. It's completed the whole passage of its wave, okay, and it's 1 second. So this is a 1 hertz wave. Now, if the wave was to do 2 passes per second, so if I was to draw another one of these, and this would still be 1 second, and it was to do 2, so up and up. Excuse my terrible wave diagram. Okay, this would be 2 Hertz because every second we are having 2 repetitions of this wave. Now, our Wi-Fi frequencies tend to happen, and I'm not going to be able to draw it because it's a little bit big, tends to happen at 2.4 gigahertz, which is 2.4 billion repetitions a second. Or we can also have the 5 gigahertz band as well in our Wi-Fi, which can happen at 5 billion times a second. This radio wave is oscillating at 5 billion times a second, and that's why we don't hear radio waves, because they're so high. I think the is it kilohertz? I think the human hearing is around about 20,000 hertz. Maybe a citation needed there. 20 kilohertz. Maybe it's 20,000 kilohertz. I can't remember, but it's significantly less than this. Now, your Wi-Fi is split into bands, so you have on the 2.4 gigahertz spectrum, where kind of 2.4 is down here and 2.5 is up here. We have it split into channels, and your Wi-Fi connection can operate in one of these channels, and let's just name them 1, 2, 3, 4, 5, 6, 7. Now what I'm saying applies to the 5 gigahertz kind of frequency band as well, but I'm not going to do it for both because the principle is the same. Now there are more channels, and the channels work slightly different than the example I'm giving, but I'm just kind of giving a very simple example here where your router, your wireless access point, can pick a channel to broadcast on. So it's picking a specific part of this 2.4 gigahertz frequency to broadcast on. So 1, 2, 3, 4, 5. So at 5, this would be, I know this diagram is not very to scale, but this could be 2.45 gigahertz, yeah? And so my router might pick channel 3, and it might broadcast over here. Now, if everyone is broadcasting in channel 3, then we're all using the same radio waves, and the signal can get very muddy, and there can be a lot of interference. So if I've got others broadcasting here as well, and they're all using this, then there's a lot of interference in this channel. And so what I can do is I can change my channel, and I can broadcast on one that isn't being used and a frequency space that isn't being used, which means that the frequencies won't interfere with each other. So I can kind of not be interrupted by what's going on here. And you could think of it like a note playing. So if I was to play the same note at different rhythms but the same note, it would start getting confusing as to they would start to kind of merge together. Whereas if I was playing a kind of high note and a bass note, you would clearly hear them as separate notes, and that's kind of the same thing that we've got going here. If we've got a different frequency, then it's not going to get muddled up with all of the radio waves broadcasting at the same frequency. And so we can think of our network in terms of frequency. So they connect on the 2.4 gigahertz and the 5 gigahertz frequencies of radio waves. Hertz referring to how many times it oscillates per second, the radio wave, okay, and gigahertz being billions of hertz, or billions of times per second, sorry. And we can think of those frequencies as being split into channels that we can use rather than it just being one big frequency that everyone connects to. It's split into channels that makes it easier to separate networks and get kind of performance boosts for a Wi-Fi network. Okay, so let's go back to here. Do give this video, maybe watch the first kind of minute of this video and see what you think. So let's talk about encryption. Encryption is a method for scrambling data with a key code which makes no sense. On an open or public Wi-Fi network, anyone can join and sniff out packets of data from other users. Therefore, encryption is used. If intercepted, the data will have no meaning. In order to read the data, the user is required to decrypt the data using the key. When you are using a secure site, for example your bank, or purchasing on Amazon, encryption applied to keep your details safe. The encryption method is called SSL, Secure Socket Layer. A tiny padlock appears in your browser window, usually on the left-hand side of the address bar, and the website address starts with https://. So here's an example of Twitter. Okay, we've got the padlock up there, and it's https. Now you'll remember back to last lesson when I gave this HTTP as the protocol, okay, Hypertext Transfer Protocol. It also has a big brother, or maybe a little brother, because it's newer, I guess a little brother, but I wouldn't say big brother because it's like stronger. The analogy is useless, but we can use Hypertext Transfer Protocol with a secure socket layer. And so let's grab my brush. So with secure socket layer, or SSL, and the fact that we're using, sorry, I've kind of butchered that. The fact that we are using SSL in HTTP is denoted by having an S after the HTTP to say that we are or we aren't using a secure socket layer. So if I just get rid of this and secure socket layer. So we can refer to this as HTTPS, which is a kind of boosted version of HTTP. The difference is that HTTP is not using encryption. So anything that I send, so when I use HTTP here, I'm sending plain data across the web, and this website is coming back to me as plain data. So if I was to type in here http ://ocr.org. Oh, that's not OCR. Have they had their domain name bought by someone else? That's embarrassing. They put that in their own OCR. No, just OCR. .org.uk. Okay, I'll let them off. So you can see here that I've got the padlock and I've got HTTPS. I don't think it's possible for me to access a HTTP version yet. It keeps forwarding me to an HTTPS. But if we did go to http://focusedongirls.kent.school.uk, you can see that I now have this not secure. And so the Folks and Girls website is actually just sending over HTTP. Now, why would a school think that this is acceptable? Surely they would want to be protecting their students. The answer is that this is just a web page. So I'm not putting in any personal information, and so it doesn't matter if I am receiving this in plain text. It's there for anyone to see anyway. I can go onto this in any network and find this website. And so this is not a problem that someone can see that this web page is being sent to me, because it's just a web page. As soon as I go to something like my account and go to, I don't know, webmail, will that automatically sign me in? No. Cool. So you can see here now I've got this padlock, and now I've got this HTTPS, because this is where I can type things in and actually send data across. And so that's important to have this encrypted channel, this HTTPS, that allows my data to be safe when traveling through the internet. So Twitter uses a hypertext transfer protocol with secure socket layer when you log in. Why? Why does the data need to be encrypted? What could happen if it was not encrypted? Well, here, let's go back. Here I can put in my phone number, my email or my username, and my password. So I could potentially be sending my phone number and a password, or an email address and a password, through the internet unencrypted. And if I was doing that, then that could have all sorts of implications for if someone was to find that combination. If I was using that password with other accounts, they could use that and try and hack into other accounts. If I'm new to Twitter and I've put in my full name, my email and my password, they have an extra bit of information as well if I've sent that through the internet to Twitter. And so making sure that it's encrypted and that only the right people can view it is really important. And even if I'm broadcasting over a wireless network here, and someone is in the middle trying to intercept my data and trying to convert it to streams of data that they can kind of then use, they're not going to get very far because it is encrypted. And encryption does something really nice. It takes a kind of plain text phrase, so let's say the words, what should my username be? Let's just say a simple word, so hello. And it takes that and it transforms it into something that is completely unlike the first thing. So maybe I get like X10 J5. Okay, don't ask me. I just kind of made that up. There's no kind of process that I used there. But you can see that this now, if I got X10J5, I wouldn't immediately think, oh, that probably represents hello. Okay, and so we've encrypted it and it's completely abstracted away from what the original message was. So watch this encryption video, have a look at it, and it's quite a good video. And then come back. I will wait here for you. Pause the video though, I'm not going to wait that long. Pause this video and then watch the other video. Yeah, cool. Okay, so quick recap on keywords. Topology, so how a network is physically laid out. A mesh network, a network where computers are connected to, or nodes are connected to devices that they typically share more data with. And nodes can be connected to more than one other node. Star network, nodes are connected to a central server. Wi-Fi, wireless frequency, allows devices to connect without a cable. Encryption is a way of taking data and transforming it into an unreadable form so that someone doesn't know what they're looking at. And Ethernet is a standard which typically uses copper cables in order to allow computers to be wired together. Cool. So that's the end. I would like you to make sure that you took notes, make sure you took part in the activity. And now, if you want to, you could think about coding an encryption program using a programming language of your choice. So take an input of plain text, do some kind of process on it, and do an output of encrypted text. And I'll put a video on here, a separate video about kind of how you could write a small encryption program as well to give you some kind of starters. Okay, sweet.